Hi, in this video we're looking at logarithms. We're looking at the scenarios in which it may be used, what are some of the special rules around it, and I do an interpretive dance to show you how good it is at making really large numbers become small. I'm sure you're curious about it, so let's get into this video. What is a logarithm? As soon as humanity learned to add numbers, it found a way to simplify the notation for adding the same number several times. For instance, if I want to add 6 plus 6 plus 6 plus 6 plus 6 plus 6 plus 6, that is, add 6 7 times, well, I don't have to go and do 6 plus 6 plus 6 plus 6. I can do 6 times 7 since I'm doing it 7 times. So we got multiplication. Then an obvious question appeared. How could we write multiplying the same number several times? So we've gone ahead and used multiplication for when we want to add the same number several times. But what about when we want to multiply the same number several times? So if I want to, instead of 6 plus 6 plus 6 plus 6 plus 6 plus 6 7 times, what if I want to do 6 times 6 times 6 times 6 times 6 times 6 7 times? Well, in that case, we can use something called exponents. It will be 6 to the power of 7, an exponent. However, there is always that one curious person who asks the wildest questions. In this case, they wondered, is there a way to reverse the reaction? Reverse the equation, the operation, invert it? Is there a way? Well, there is a way. If you added 6 plus 6 plus 6 plus 6 plus 6 plus 6 7 times, you can subtract it 7 times to reverse or invert the operation. Now, if you multiplied, in this instance, as an example, the 6 times 6 times 6 times 6 times 6 times 6, reversing that operation, referred to as inverting, is division. You divide it. But what about in the case where we did exponents, so we raised it to the power of a number when we were multiplying the same number multiple times? That would be a problem because while 6 plus 7 is the same as 7 plus 6, or while 7 times 6 is the same as 6 times 6, 7 to the power of 6 is very different to 6 to the power of 7. So inverting that equation or reversing that equation would not be so straightforward. For exponents, enter the logarithm. The logarithm is the operation you will choose if we want to reverse a function, invert a function, so that it tells you what the exponent you need to raise a number to obtain a value. Here are some vital information about the new friend we've just made, the logarithm function. In general, there are two very special cases of the logarithm. There is the natural logarithm, which is noted as ln with x in bracket, and then there's the logarithm with a base of 10, which is denoted as log in brackets x. And the x in the case of the natural logarithm is this number called an Euler number. And the x in the logarithm to the base 10 is, guess, 10 to the base 10. The value for x is 10. An important characteristic of this logarithm function is that the logarithm function is defined only for positive numbers. So in other words, if we write log a with b in brackets, then the b has to be, which is the x, has to be a positive number. Don't forget, this is more like a memorizing thing. The logarithm of 1 is equal to 0. So whenever there's a logarithm of 1, it's equal to 0. And this kind of makes sense because whatever you raise to the power of 0, you get 1. Another important characteristic of logarithms is that they're very important. They're extremely important. So outside of mathematics, they're used in statistics, the log normal distribution. They're used in economy, the GDP index. They're used in medicine, the quick eye index, and in chemistry, such as for half-life decay. And as mentioned in my video on the history of logarithm, it's a bit of a windy video, but if you want to hear lots about logarithms, the logarithm is used in a few physical units, such as the Richter scale, the pH scale, etc. There is a special case of the logarithm, which is sometimes used. It's not as default as the log to the base 10 or the natural log. And this case is log to the base 2, which is also sometimes called the binary logarithm. So let's make this concrete. If we want to know log 10, so log to the base of 10 of 8, we put into the calculator log 10 and 8, but if you're using a phone calculator, then you actually have to put the 8 first and do the log to the base 10, and you see that the answer is 0.9. Excellent. Now let's just double it. Let's double the value. So we're going to 16, and we go ahead and do log to the base of 10 of 16, and you see that the answer is 1.2. How about if we double it again and we go log to the base of 10 of 32, we get 1.5. Interesting. Log, by doubling again, we do log 10 of 64, we get only 1.8. What if we just really get a much larger number and say log to the base 10 of 1064, we see 3.02. So what does this mean? What are we doing exactly? What's important to take from this, or what you should grasp from this, is that as our x value, the value that we wish to ascertain the log 10 to the base of, as it doubles, the output y is only increasing marginally. Like it's only increasing by 0.3 if we are just doubling. The effect of this is that as our values increase and become massive, our output, our y, becomes comparatively tiny. It's comparatively tiny. It's not scaling as astronomically as our value. So when we went from a 64, a log to the base 10 of 64, to a log to the base 10 of 1064, we saw that we only jumped from 1.8 to 3.02. And so we are able to keep the output scale comparatively tiny, even though our inputs, our values, our x is large. And this can be really useful when you're dealing with really large numbers, really large, cell numbers, or you're talking about viral particles, viral infections, where you may have lots of viruses, and you're trying to put it on the same scale, you're trying to communicate it and really track what's happening. Then by logging it, you're able to keep the output values relatively tiny, even when the input values going into it are ginormous. Well, that brings us to the end of this video. I hope it was useful. If it was, please consider liking and sharing with anyone who you know gets logarithms but doesn't really get logarithm like all of us, right? And yeah, thank you for checking out the video. All the best with your calculations and your data analysis. Bye.